So this is Unit 3. We're looking at Section 3, where we're going to talk a little bit more about gas laws. Notice this is number density. The further you come towards the sea level, the higher the number density. That means there's more, the air particles are more concentrated. Again, number density is calculated by N, which is the number of particles, divided by the volume of space that the particles are contained in. When you're actually using a barometer, you are measuring air pressure by the height of this column. So as this slide implies, if the air on the outside is high, so if you have a high pressure sunny day, that air, the way the air particles will push down on this dish, then causing the height of this column to rise. So that's what they mean by the air pressure is rising as we go towards a higher pressure system. This is equivalent to that activity we did in class where we created sort of a U-tube and we manipulated the differences in pressure at these 2 points. So if we left these two open to regular room air pressure, these two liquid levels would be even. However, if we remember, we used a syringe and we literally suctioned out some of the air particles that forced the air pressure to lower over here, meaning that the pressure was higher on this side, so pushing this down and causing this to go up. Very, very similar to this. Wanted you to make that lab to reality connection once again. A few terms you need to know. STP represents 273 Kelvin and 1 atmosphere pressure. So STP really represents two values, the temperature and the pressure. Also at STP, we know that a mole of gas excuse me, contains 6.02 times 10 to the 23 particles. That's a lot of particles, and it takes up the space of about 11 2-liter Coke bottles. That's interesting. And it doesn't matter what type of gas, whether it's neon or helium or carbon dioxide. At STP, these values remain constant. By the way, 6.02 times 10 to the 23 is also known as Avogadro's number. Now for some practice. Let's see if you understand these concepts. Which contains more molecules at STP, a mole of xenon or a mole of neon? If you said the same, you were right, because as Avogadro's law implies, it doesn't matter what gas you have, they will have the same number of particles at STP. For a mole. Which takes up more space at STP, a mole of nitrogen gas or a mole of neon gas? Again, if you said the same, you were right, because according to Avogadro's law, a mole of gas at STP would take up 22.4 liters of space. Question number 3. Which gas contains more atoms? A mole of nitrogen or a mole of neon? Okay, the correct answer, a mole of nitrogen. Reason? Nitrogen, each molecule contains 2 atoms. Recall the Lewis dot structure. You actually have 2 atoms in the molecule, so you have double the number of atoms. So this has 12 times 10 to the 23rd roughly, versus neon, which would have 6.02 times 10 to the 23rd atoms. Ideal gas law, PV equals nRT. Okay, this problem is from page 334, number 6. It reads, how many moles, So let's go through this. That's N of helium are contained in 10,000 liters. That's volume. In a 10,000 liter balloon at 1 atmosphere. That's pressure. And 10 Celsius. That is temperature. Note that this has to be converted to Kelvin, so we'll go ahead and do that. 283 Kelvin. So we have R here. That's a constant that would be given to you on a formula sheet. So we simply need to solve for N here. Okay, so start with PV equals nRT, dividing both sides by RT. We have N equals PV over RT. So you can plug in at this point 1 atmosphere times the volume, which is 10,000, divided by, this is R, 0.082, and the temperature being 283. Okay. So I'm just running that calculation. That comes out roughly to be about 431 moles of helium, and that seems like a lot, but we're filling a weather balloon, so it's not just, you know, your garden variety happy birthday balloon. Okay, 431 moles of helium. All right, humidity. So you step out on a hot day and you notice that you're just sticky all over. What's that about? Well, what's happening is the evaporation. The number of water particles that actually evaporate into the air is much greater than the number of water particles that are condensing from gas back to liquid phase in that water puddle, for example. So if you look at this graph right here, it's kind of interesting because you can actually measure that amount of water vapor in the air. We measure that in terms of a term we call humidity. So humidity and water vapor density. So the higher the temperature, the more water vapor the air has in it. And this curved line right here actually tells you the 100% humidity line. So let's say, for example, if it is right now outside, if it's 0 Celsius out, you can't really hold a lot of water vapor. In other words, there's not as much evaporation going on. So you can have 100% humidity, but that doesn't mean you have a whole lot of water particles at that temperature. However, as it gets, that's why you perhaps don't feel sticky when you step outside on a winter day like today. However, if you could imagine yourself on a June day when it's possibly somewhere 25 to 30 degrees. Now notice you can hold a lot more water vapor, and that's the reason why you might feel a little bit sticky on a very, very warm day, especially near a source of water like a lake or an ocean. Something we're not that familiar with in Michigan would be hurricanes, so you can imagine. We need to go over this a little bit. Interesting thing about hurricanes, the energy is generated from the warm oceans. And this energy, you may have heard meteorologists talk about how it feeds it is fuel for this hurricane, and how it feeds the hurricane to make it strengthen. So in actuality, you have the warm, moist air rising, and then as it rises, it actually warms some of the cooler air above. That causes the cool air above to rise even further. Now, when you get to a certain point of coolness, that cool air actually descends or falls, and as it falls, it actually is also releasing more warm air. So this is a vicious cycle where this constant rising of the warm, humid air then goes through the cycle of then cooling again, and each time things cool, they send energy outwards, and this energy in turn causes the moisture in the air to become more and more, as well as the speed of the winds to increase. And so this constant addition of moisture and heat is what generates these fairly large hurricanes that take over sometimes a lot of area, and also end up picking up speeds to 130, 150 miles per hour, and it can be very, very devastating.